go out of this PowerPoint presentation, this whole thing again, because I need to share my screen. We're recording. Okay. All right, now that it's on record, again, set some goal. If you don't work hard, I'm gonna fail you. If you do not have basic computer knowledge, do catch up real quick. For those of you who have to somehow answer a question that you feel like this can be Google in 5 minutes, don't answer that. It's wasting your time. Your friends are basically asking you to do his or her job. So don't do that. Grow up, do your work, and be motivated. This is the reason why you should do any graduate level degree. Please be motivated. Okay, so let's come back to our topic in the class. What happened upon the last level cache misses? Basically, when you have a data request, right? And we've been developing our, I guess our computer from the processor inside outward, right? We have the pipeline, we have the processor, we have the branch predictor, we have the cache. All the caches that we talked so far is on chip. Everything is inside the CPU package that you buy, right? If you go to any shopping that like IT store and you say, I want to buy a CPU, Intel CPU, AMD CPU, those comes with everything we covered so far, right? The actual pipeline, the data forwarding, branch prediction, out of order scheduling, caches, instruction cache, data cache, TLB, those are all on the chip, right? The reason why they're on the chip is because they need to make it really fast. So what happens when you require some address? Your actual physical location of your data is actually off the chip. There's actually a nice like breakdown between on-chip stuff and the off-chip stuff, right? When you buy DRAM, where do you plug that DRAM DIMM in? So the stick that you buy, the DRAM stick or memory stick, whatever you call it, the official name for that thing is called DIMM, D-I-M-M. Where do you plug it in?
Motherboard.
Yeah, you plug it on your motherboard, right? It's a totally separate location. It's totally separate physical location between your CPU and your motherboard. So similar to the SRAM cache, right? DRAM also has limited capacity and limited bandwidth, right? So today it's pretty clear. So anyone has a question about why DRAM has limited capacity? So that should be pretty simple to understand, right? That's a certain size to your DRAM. You can't pack any more transistors. So it's 8 GB, 16 GB, 32 GB per DIMM. And these days, this number will keep going up because of how the memory scale. So technology scaling is a terminology that means that as time progress, right, we are doing better and better at improving technology. And one way we can improve is make the transistor smaller, which means that you can pack more transistor and capacitor on your DRAM, which means it's going to get bigger and bigger. So today we will talk about what do I mean by limited bandwidth, right? How do you access DRAM? And also what make things longer and what would be faster to do when you have to access memory. But before we begin, the first thing that we need to talk about is called the MSHR, or it stands for miss. Oops, I need my pen. So give me the pen. Miss status handling register. MSHR. What do they do? So typically, without the MSHR, what happens when when you have a cache misses, right? What will happen to cache miss on the same block? Basically, they request the same not the same exact address, but it's the same cache blocks. What happened? There's already, say, request 1 and request 2, right? This come first, request 1 come first. It requests cache block 1, and request 2 that come afterward just happen to arrive and say, hey, I want that too. Do I need to send 2 active requests to DRAM saying, hey, I need cache block 1? Do I need to do that? Or can I just say, hey, I'm gonna wait until request 1 got its own cache block that they are going to be in the cache, right? So I'm gonna wait for that in the cache and I'm gonna get that data. Should I send another request or it's okay? Anyone want to take a guess?
Send waiting for the cache block.
Yeah, you just wait for the cache block. Why bother sending another request to the same data, right? So that's basically the question I was asking. So a better question is, how should I handle a cache miss? Right? How should I handle a cache miss? And our MSHR is kind of like the solution to these questions. Basically, it's a design to help allowing the processor to handle the cache miss better, more efficient. So what is the MSHR? The way it works is when you have a cache miss, you store the miss-related information. What are those information? And why do you have to store them? So the reason why you have to store them are, you store who demands the data. CPU 1, CPU 2, CPU 3, etc. Right? Let's say you have 4 core. Is it core 1 and core 3 that wants the data? Why do you need that? So that you can forward it back to the CPU that requests the data. You know who needs it. So that you can send it back to the CPU that requests the data. Right? Another reason is the misrelated information is stored the address. So you know the ongoing cache misses that are being resolved, right? This can be on any cache level between L1 and L2 and L2 and last level cache and the last level cache in DRAM. And because of the answer to our question, it can eliminate redundant work. The request that wants the same cache block will be merged, if you want, if you say so. Basically, they are being merged into one single request. When the data comes back, that request go into and notify the MSHR saying, hey, that address come back. Whoever needs the data is on this cache block right here. And the number of the MSHR entries, this is the limiting factor to how many requests you can have to DRAM in flight, right? Because the reason is all cache misses allocate entry in MSHR. So let's say I have 32 entry MSHR. How many requests I can send to DRAM at maximum? 32. I will have 32 ongoing requests up to 32, and any more than that, wait. There'll be a queue to basically wait for the free up MSHR entry. And inside the MSHR, basically the processor that requests the data information goes here. This is the address, right? So that you know what cache block you are fetching. And any metadata related to the cache access, right? Basically, any additional information that you might need, things like a valid bit, and whether this is a read or write request, right? So that you know what's going on for that cache block accesses. Any question before we go into the actual topic that we need to discuss today? So think of it this way. The MHHR that we just talked about is basically a buffer area for all ongoing DRAM requests. It acts as this buffer area for keeping track of our ongoing DRAM requests. So before we understand how this works, we first need to, or I would first need to kind of introduce what the heck is DRAM, right? So the first thing I need to tell you is there's this unit called DIMM. Whenever you buy DRAM, that one memory stick, whatever the language we use in Thai, I don't even know the word, but the official word is one DIMM, D-I-M-M. Each DRAM DIMM is connected to a processor side through what we call a memory controller. We'll go into the detail today. Each DIMM can be broken down to a small units from channel, rank, bank, row, and DRAM cell. So this is bigger. The top thing is the larger one. The bottom thing is the smallest unit inside DRAM. DIMM stand for Dual Inline Memory Module. Dual Inline Memory Module, and I'll tell you what it means. During each time interval, DRAM can only transfer basically a limited amount of data, right? And this is the bandwidth as we know it. There's a certain bus that connects the DRAM DIMM to the processor. That bus has certain bits. It can transfer limited amount of electrons. Anyone want to take a guess of where is that bus on your motherboard? So when you buy a DRAM, so let me switch over to home so that I can show you DRAM DIMM. So you see these chip, right, from my screen. Yes, no. You see the screen that show Google Chrome and DRAM DIMM. So this whole thing, you see my mouse? So this whole thing is called a DRAM DIMM. These are different chips. These are what we store the data with. Basically, we store the data on this chip. I believe this is error correction DIMM, which we'll go into the detail because there are 9 chips instead of 8 chips. The extra chips is to add what we call the error correction bits, so it can self-correct the error. Over here, you see this copper looking thing, right? This copper looking thing. This is where you connect, this is literally the wires that connects your DRAM DIMM to the motherboard wires that connects to the processor. So you see the actual connection from here to the chip, right? From here to the chip. So this is where electrons move from DRAM down to the processor. Anyone want to take a guess on why are there certain lengths of this connector pins? And basically, these are called pins, right? These are what limit the amount of data you can transfer between DRAM and your processor. Anyone want to take a guess on why, if that is one factor that limits your bandwidth, why haven't we have a really long DRAM yet? Anyone want to take a guess?
It's too far to electron to move.
Yeah, so that's actually part of the reason. The main reason has to do with cost. You have a certain amount of land, I guess, on your motherboard. So if you use it for DRAM, you need to figure out how you're gonna wire everything around that too, right? Are you gonna have fewer PCIe connection? So these pins turns out to be what is one of the most costly things to have in the memory subsystem. So this is like a cost has to do with this number of pins quite a lot. And because these are physical connection, it's really hard to make this pin smaller as well. Because if you make it too small, they would short circuit. Right? So there's certain size you can have for the pins. So I'm gonna go back to the slides now that you see the DIMM. So this is basically what limits the bandwidth. And there's the certain amount of parallelism, which we will call memory level parallelism. Because memory take a long time to access, right? One of the big idea in dealing with these data access is, well, if they take a long time, I'm going to service a bunch of requests in parallel. And today we'll learn how that can be done. Basically, now that you have the MHHR, and let's say it has 32 or 64 entry, which means that from the processor side, I can request 32 data access or 64 data access at the same time. Anyone want to guess what type of architecture is having would like to have a lot of bandwidth, a lot of parallel memory accesses? What type of processor architecture would like to have that? Is the GPU, right? The GPU, one of the limiting factors is how much bandwidth you can give to the GPU itself. This determine basically how much throughput you can have. Once we are on the GPU lecture, you have more idea of, okay, this is why you need to have a really high bandwidth DRAM, because the GPU issues so many memory requests compared to a CPU application. And the answer is yes, we can build the DRAM that way. Basically, the structure is it internally is designed to provide high level of parallelism. So let's go over the high low of DRAM. So let's say you buy the DRAM, two DIMMs, right? And you have the processor. The channel is the physical channel. So how many of you look at the motherboard and notice there are two colors? So if you have a desktop next to you, when you're free, feel free to open it up. If you have 4 slots that you can plug the DRAM in, you will notice they have two colors. Those color, each color is different channel. Basically, each color is a different channel. And my recommendation is make sure you put the DIMM into 2 separate channels, because these provide the most bandwidth. After we go into this lecture, you know how and why, right? You understand why you should do that. Why, when you look at the motherboard specification, they'll tell you exactly this is what you should do when you buy DRAM. Plug it in these configurations. It will give you the most bandwidth. It will give you the most performance out of your DRAM. Each channel share the same clock. Each channel share the same clock. They share the same data bus. They share the same command bus, the command that drives DRAM. So channel 0 has its own data bus. Channel 1 has also its own data bus. If you plug DRAM into 2 different channels, double the bandwidth. If you want to zoom into DRAM, right? Basically, there's a front side and a back side of DRAM. Now that we are diving down from channel, DRAM channel to DRAM rank. So one thing you might have noticed is there's a bunch of chips on DRAM, right? Right. Basically, when you buy DRAM, there's a bunch of black chips on there. And I told you that this is where you store the data. If you look at both sides of DRAM, both sides has its own chip. These are two separate chips. These are two separate chips. It's not one single chip somehow on DRAM that basically go through this green thing. They are two separate chips. The front side and the back side operate in different rank. This is actually the reason why we call it dual inline memory module. This black thing is a chip. And if you zoom in, basically if you zoom in and you want to transfer the data over, right? So let's say DRAM speed is 2666. So how many of you see that? DDR4 DRAM 2666. That's one possible specification. Again, let me use Google Chrome to show you an example of that. Let me go find DDR4 DRAM on Amazon. Here is one example, right? You see some laptop DRAM with 2666 megahertz. Actually, this is a lie. It's actually not 2666 megahertz. It's actually half of that. I'm gonna go back to my slide. You notice the number that I highlight, right? 2666. The way it works is if the specification is this, the clock is actually 1333. The clock, when you look at the signal, it looks like this. There's a positive edge and negative edge of the clock, right? These are the value 0 and this is the value 1. So it's gonna, the clock would switch between 0, 1, 0, 1, 0, 1, 0, 1. One cycle is this whole thing. This is one cycle. The reason why they claim is 2666 is basically you can subdivide this. Rank 0 and rank 1 will burst out the data in the positive and negative edge part of the cycle. That's why it's called dual inline memory module. Within the same data bus, it used the positive and negative part, positive edge and the negative edge of the clock. You can burst out two ranks in one cycle. That's why you can claim that it's 2666. Any questions so far about how DRAM works? Because we are going to keep diving in. All right, so let's zoom into the chip, the black thing that you see. Inside the black thing, this is what is inside. There will be a lot of DRAM banks. These banks operate in parallel. So if you have an access to the address here in the bank 0, you can service them and send out the data in parallel with another address in bank 2. So if I have 8 banks, how many parallel DRAM requests I can service at the same time? If I have 8 banks. 8, yes. Yeah, 8, you're correct. You can service 8 parallel DRAM requests in one cycle, but they share the command bus. So you need to queue up to say, hey, this cycle say, hey, I need that bank 0. The next cycle say, I need data from bank 1. The next cycle I say, I need data from bank 2. So you need to take turn sending the commands in, but command is quick. The actual getting the data is long. It takes longer. So this is the chip, right? And you notice there are 8 chips, right? Yeah, 8 chips. How big is a cache block? Let's go back to our caching lecture. How big is my cache block? 64, right? 64 bytes. So if you have 8 chips, the way it works is every single chip work in lockstep. They work together. So when you request address 1 from bank 0, this chip will send only 8 bytes of data. Oops. They will only send 8 bytes of data. And together, 8 of them, each one of these will be sending 8 bytes. So each of these will be 8 byte, 8 byte, 8, 8, 8, 8, 8, 8 byte. So what's the combined data, like the width of the data that I got out when I combined everything here? 8 multiplied by 8, right? Which is 64 bytes of data, one cache block. One cache block. In one cycle, it's actually in reality, it depends on how you control. In one cycle, it might not be the whole entire 8 bytes. It might be bursting out 1 byte at a time, 8 bits, 8 bits, 8 bits, 8 bits, 16 bits. Basically, the way you look at this is each chip will give you a fraction of the address of the cache block that you request. Right? So this is called DRAM banks and how it works across all the chips in the rank. And the DRAM channel, which is the biggest unit that I talked so far, right, is physically connected to the processor. So it has its own data bus, command bus, and address bus. The channel is physically independent from other channels. So let's say you buy multiple DRAM DIMM, make sure you spread it out across all the channels you have on your motherboard. It has its own memory controller, which means that you can clock DRAM in a different channel with different timing, right? And it sends a series of DRAM command to read write data into the DRAM cell. DRAM rank, as I said earlier, contains multiple chips and they work together as a rank, right? So a rank is a word referred to a unit in the military. So a unit in the military is when a bunch of soldiers work together, they work as a rank, right? They work as a team. They will do things together. So basically, these would work together to send and retrieve data from the ship. And because the RAM clock is slower than the CPU clock, multiple rank can utilize the bus while other rank is busy. And this is fundamental concept behind the DIMM, as I said earlier, the positive and negative edge of the clock. And DRAM bank inside the chip distributed a bunch of data across different banks. Different banks can transfer the data in parallel. But as I said, that's a shared command bus, so you can only send one command at a time. And the controller, the memory controller, is responsible to send out these commands. So if you start reading papers on memory, there'll be a big topic on memory controller. I myself have been working on this topic quite a bit as well. So any question about DRAM before we go into the memory controller? All right, this is no question. Basically, let's talk about this concept called bank level parallelism, which is what we got from the fact that we have multiple banks and they can operate in parallel. Basically, you can basically, the way the memory request works after, right? After you got a request from the cache saying, hey, I need that cache block. There'll be an area where you store all these requests, and inside DRAM, right now it's actually on the motherboard side, there'll be a memory controller that say, hey, given all these requests, which one should I service first, which one to send to different banks? And you can send these accesses across multiple banks in parallel. Right? This is called bank level parallelisms. Each bank contains multiple DRAM rows. Inside the DRAM structure, charges are stored in DRAM cell. That is too small to be sensed, right? Anyone want to take a guess on how many electrons is in that capacitor inside DRAM? Actually, I'm not sure how can you guess that correctly. So let me tell you the number. It's actually less than 10 electrons. So you need to be able to tell how many electrons you have inside that DRAM, like a tiny, tiny, tiny DRAM cell. And this charge needs to be amplified because you can't tell, right? It's too small. So you first need to amplify. We'll go into the detail on how this process is done. But when you amplify this, they are being forwarded to this unit called the row buffer, right? Which can be further broken down to local and global row buffer so that we can sense the electron easier from the controller point of view. DRAM will use what we call sense amplifier to amplify the data. This sense amplifier works way as a normal amplifier, right? So in music, what is amplifiers used for?
Increase the volume.
Increase the volume, right? The way it increases the volume is it increases the amplitude of the signal, right? Hopefully, a good amplifier will make sure when you increase the volume, every signal integrity look the same. You don't change the way music behave, right? You don't change the signal. You don't randomly change different frequency range in different amplification. But basically amplify them all equally. This is the same thing in DRAM. You want to make sure you have the amplifier that amplify the data without introducing any errors. Only the data in the row buffer can be read because they're so small. You need to amplify so that you can read it. So if you want to have the high level, I guess, overview of the DRAM bank, you can break it down into this 2D cell array, right? There are multiple row. So this is row. And there are also multiple column. This is column. And these are the row buffer. So the way it works is when you want to read something, the controller will say, okay, I need to say read that row because I want this cache block. Let's say I want this cache block. What will happen is this entire row will be put here. So this whole thing will be moved here into this row buffer so that you can read from this third cache block, right? From this third cache block. The thing at the bottom is a row buffer. Is the signal there is amplified enough that you can read from it. So the operations here, there are basically two status of the row buffer, right? There can be open and there can be closed. The row buffer, if you look here, open row buffer means that I just move some certain row of data into the row buffer. Which means that once I'm done reading this block, and let's say I want to read the green block here, right? Green block here. I don't have to do anything. I don't have to move the data again from that row into the row buffer because it's already there, right? It's already right there. So that's when the row buffer is open. And that's some readable data in the row buffer. A closed row buffer means that I already moved the data in the row back, move it back to the cell. The reason why you need to move it back again is because the cell is so small. When you move something out into the row buffer, you lose all the data in the cell, so you need to write it back to the cell. This process is called closing the row, right? DRAM need to spend some time moving that charge that you amplify back from the row buffer to the cell array because there's not that many electrons. I need to make sure I move it back to the row. To read a row, it means that you have to make sure the data is already in the open row buffer, right? So if you want to summarize, basically, if you need to read data in an open row, right? If you need to read the data in the row buffer, that is already there. That's already there. The only thing you have to do, spend time reading that data. Spend time reading that data. All right? If you need to read the data and the row is closed, if the row is closed, there are two steps. First, you need to move the data from the DRAM array to the row buffer. Then read it. Two steps. Move the data into the row buffer, then read it. The third case is, let's say I have an open row here. So let's say I have, this is my DRAM cell, this is a row buffer, and it's having row A. But for some reason, let's say my cache block that I need to read is row B over here. And row A is actually now located here. This is row A, right? What I need to do here is first, because row A in the DRAM array already lose all the data. So the first thing I have to do is to move the content of the row buffer, everything here, move it to row A so I can store my data in the DRAM array. So this is the first step, right? This is called closing the row. I close the row so that row A's data is moving back to DRAM. The next step that I have to do is, okay, I need to read row B, all right? So I need to move this blue thing into here. So that's a second step. This thing becomes blue. The third step is simple. Basically, now you know you need to read that cache block. So that's our third step. Read that part in the row buffer. So if you need to read the data in a different row than an open row, you need to move the data back, bring in the correct row, and read that row, right? 3 steps. 1 step, 2 step, 3 step. This is called row buffer miss. This is typically called row buffer hit, right? If you look into my earlier lectures, whenever I talk about the memory, I have been saying that DRAM accesses take roughly 12 nanosecond to 50 nanosecond, right? Anyone want to take a guess on why is it 12 nanosecond and why it sometimes is 50 nanosecond from this slide? So what is a case where it only takes 12 nanosecond?
Sometimes if the long and if it contain more electron to collect the same area.
No.
No.
No. If you look at this data, what is the fastest scenario that can happen when I need something from DRAM? What would be the fastest scenario?
If the row is already open.
Yes, the row is already open and the data I'm reading is from that open row, right? Row buffer hits take roughly, I think these days probably like around 10 nanosecond. So what would be the case where it takes 50 or more? The third case, right, where you need to move whatever is open row back to DRAM, move the correct address row in row buffer and read it. So there are 3 steps over there and take more time for sure. Outside of these 3 cases, there are other requirements that govern DRAM timing, which some of them we will cover, some of them we will not cover because that's basically way too much detail. But let's look at the basic operation. So if you read DRAM specification sheet, again, let me borrow Google Chrome. If I go to one of the website, jip.com, which sell a bunch of DRAM, and I'll randomly pick one of these DRAM, and I'm hoping they'll have the timing for me. Here. Okay, not good. Let me go to a better website. All right, despite the fact with all these possible coupon that I can have, I cannot buy them. So you see this cache latency, right? Cache latency, this thing. This is actually CAS stand for column access stroke. This is how much it takes to just read the data, right? So if we go back to our slide, this is the time TCAS, right? The same keyword TCAS, or sometimes we call it row to column RC, sorry, RCD. This is the time it takes to, once we have the data in the row buffer, this is the time it takes to read the cache block and send it to the cache. There's another time called pre-charge. Pre-charge is the process of moving whatever's in the open row back to DRAM, right? This is, if you have a row buffer miss, this is the step 1. You need to pre-charge the row buffer, prepare the row buffer for the next row of data. This basically means that if you have data in the open row, move it back to the DRAM cell. Then there's an activate row access stroke RAS. These move the target row of data you want to read into the row buffer. So if you have a row buffer miss which has step 1, step 2, and step 3, this is step 2 and this is step 3. You pre-charge, activate, then read and write, right? So this is the normal sequence: pre-charge, activate, read, pre-charge, activate, read. If you have a row buffer hit, right? Row buffer hit. Basically, this means that you only need to do step 3. If you have access to close DRAM row, you only have to do step 2 because you need to activate then 3. The last case, it means that our controller basically will proactively close the row by pre-charging and move that DRAM row data back to the cell. What would be the likelihood of that? If I know that I'm likely to not have to use that data in the row before, you can proactively close the row, right? So as I said, pre-charge can be done preemptively, right? That's a latency when you have to read and write things. That's a write to read latency, TWR, and write to pre-charge, TWP, that you have to wait. basically the two numbers will be the additional time you have to wait if you need to switch between write to read or write to pre-charge. If you do not wait, it means that you're introducing error. Basically, you don't give the DRAM enough time to move the electron back. If you do not wait this amount of time, you are going to have fewer electrons than expected, right? So it means that you are likely to have errors. Then there's a bus latency, how much time it takes to transfer the actual data once it becomes ready from the TGGS, right, to DRAM across the chip to the bus. Here's the operation. I'm going to borrow the figure from my friend's paper. So this is the paper from one of the paper from our my PhD group back in CMU. As I said, we work on tons of DRAM topic. Our group, my advisors group, is essentially one of the biggest research group that look into DRAM. And here's how it works, right? Notice pre-charge and pre-charge. Basically, that's one cycle, right? Notice this is the row buffer. It's a sense amplifier. This is your DRAM cell. CAP dot stand for capacitor. If you want to activate to read from, basically to move the row into the row buffer, basically what you want to do, I'm going to have the red ink here. Basically what you want to do is to move the electron here to the row buffer. What do you need to do? The first step before you can read or write from the sense amplifier, the first step is you close this gate, right? You close the gate. As you can see here, the gate at the bottom is still open. When you close the gate, what will happen? If you look at this chart, right? This whole thing is connected to half VDD. VDD is the maximum value here. Half VDD means that it's the middle between 0 volts and VDD. If my charge is greater than half VDD, it means 1. If it's lower than half VDD, it means 0. 1 and 0. Are you with me so far? So if I have a capacitor greater than half VDD, it means that this is the value 1, otherwise it's the value 0. When you connect to half VDD right here and close the gate, what will happen is this bigger capacitor here will share the charge with the DRAM capacitor, right? So if you have value greater than half VDD, this is going to be, as you can see here, is slightly more, right? Because initially this is at half VDD, right? So let me take this out. Basically, initially this capacitor has half VDD. If my DRAM capacitor is more than half VDD, you close the wire. It means they will share until the voltage value is equal, which means this big capacitor is going to be greater than half VDD. Right? It's going to be bigger than half VDD. With me so far? Then you connect this. Oops, really bad drawing here. Whether you connect this switch, what will happen is now electron from here will move in from outside from the capacitor, and based on the value, if it's greater than half VDD, the way the amplifier works here, if it's greater than half VDD, everything becomes VDD. Everything will eventually becomes VDD. So over here is still greater than half VDD, right? So at this point, it's ready to read your data. You can read the data now because it's greater than half VDD in sense amplifier. Electron will flow in. Basically, electron will be flowing into this thing. Then As you can see here, it's read and write, right? What's the next step? You need to pre-charge. If you want to switch to a different row, you need to pre-charge. So you can pre-charge by keeping this connection up. Because electron flow in here, it will flow into both capacitor, right? So your data will go into both capacitor. Once you're finishing pre-charge, TRP, right? Time pre-charge. Once you're finishing the pre-charge, you disconnect this two. This again back to half VDD. This is fully charged. To VDD. So this is the whole operations. Activate reason. Okay. TRP pre-charge, then you activate, then you read and write. Any questions so far? Okay. So from the concept that, hey, we have this row buffer, right? That's a row buffer hit. And row buffer miss. So if you access data in a row that's open, they are going to definitely be faster, right? And if you access the data in a different row, this is going to be a smaller, a slower operation. So what you need to do, or what you should do if you don't have a good cache hit rate, is at least access the data from the same row. Which means you can write your program to be aware of this. You can write your program to be aware of the fact that row buffer is 2 kilobyte or 4 kilobyte is actually a range of data, right? Make sure it's still within that range. You are going to run into a lot of cache hits and row buffer hits. So that's going to be faster. This thing is called row buffer locality, right? So if you look at the memory scheduler, they are responsible for multiple things, right? First of all, they need to make sure all the timing requirement is never violated, right? Otherwise, you get errors. The second thing is you want to maximize requests to different DRAM banks, right? Because these give parallelisms. And then you want to maximize row buffer hits, right? So this lower the latency of your DRAM access and more and more. The reason why I have and more is multiple other things. If you service certain request over another, it means that another request has to be queued up, right? Think of it this way. If you think of this as a DRAM bank as each line in the supermarket checkout, right? What you want to do in terms of scheduling is to distribute everyone across all the lanes, right? But let's say there's one lane that has a lot of row buffer miss. Everyone who is checking out that lane buy lots and lots of things, so it would take more time. Even though there's the same amount of requests going to that bank, because it's row buffer miss, the guy at the back of the line will have to wait longer. Right. So let's say each person is inside a family. So let's say I have to check out, and my family has three people in my family, all of which are checking out in the line. I cannot go home, leaving two of my family members in the checkout line. Right. It means I have to wait for the other two family members before I proceed to what we are going to do next. Right. Which means that that's also part of the queuing that can matter for performance. We will talk about this after we talk about the basic memory controller. Before we go into the controller in detail, any questions that I can answer about DRAM? Because we are switching over to more like the design part of the policy on how to schedule the request. So what we covered so far, sadly, is the knowledge that not enough people know about, but it can actually impact performance because it's another level of locality you can exploit in your program, and not many people has knowledge on, but it's pretty simple actually if you know the high level concepts. Maximize your buffer hits because you don't have to pre-charge and activate. It's as simple as that, right? Plug DRAM into different channels because you want to maximize the bandwidth. If you buy DRAM, make sure you have the same timing parameter for the DIMM that go to the same channel. Otherwise, the controller has to clock for the slowest DIMM. So these are the basics that no one, I would assure you, 99.99999% of people, at least in this country, has no idea, right? Whenever sometimes I go randomly like shopping for IT parts, and whenever I talk to the people who sell these parts to me, a lot of time I was asking questions because I was trying to find out whether I should buy this DRAM or the other one. But they cannot answer me some of those questions. I'm like, okay, I ended up having to look through my phone for the spec sheet that for the data I really want. That would answer why this DRAM DIMM cost me 1900 baht versus the other one that cost me 2500 baht, which is about 25% more, right? Are they faster? Are they faster? Why? What exact timing? Or is it because the clock is faster? Or things like that. Let's take a quick break. Right now it's 10:10. So let's meet again at 10:20. This lecture I'll have two breaks because we'll move on to the memory controller. Then we'll move on to one of the more popular topic these days. As DRAM gets bigger and bigger and bigger, they become less reliable. So we'll talk about error correction and how to make DRAM more reliable. So we'll have three sections of the lecture. Right now, we just finish the first part of the lecture. Let's do a 10-minute break. We'll meet at 10:20. Is that okay? All right. So meet you all at 10:20. Go get coffee if you need one. Okay, just enough time to make coffee. Are you all back? All right. Okay, so wait, let me check if you are back. But yeah, okay, all right, cool. Okay, so I'm going to continue talking about how the memory works by talking about another unit called the memory controller. The way it works is whenever you have a cache miss, and it wants to access DRAM, which is right here, right? Your DRAM is right here. The cache miss from the MHHR will appear as a request saying, hey, I need that address. That address the request will go into this staging area, basically called the memory request buffer. What it does is they store all the requests, so different color here are requests from different core. As you can see here, on average, there'll be a bunch of requests in the buffer, right? And because DRAM is slow, the scheduler, the job is basically pick one of these requests and send them to DRAM so that the data is forwarded back to the core that requests the data. And this will be going on until basically you turn off the computer. Everything here will happen all the time, right? Until you turn off the computer. And as you can see here, every single core 1, 2, 3, 4. Now that you have 8 cores with newer processor, 5, 6, 7, 8, they all want to use DRAM. They contend for this limited off-chip bandwidth, right? So there are multiple things that can degrade system performance, or let's say core 1, core 2, core 3, and core 4 are all running different applications. Let's say this is Chrome. This is YouTube. This is Dota 2 for some reason. And this is Microsoft Word, right? If you keep servicing Google Chrome while watching YouTube, anyone want to guess what happened? If you keep servicing Google Chrome's data without servicing the YouTube request, when you are watching YouTube, what will happen? Basically, your YouTube video will stop playing, right? Your YouTube video will stop playing, even though you try to service Google Chrome, because YouTube is a different thread that wants its own data, which means this is a pretty useless policy. So you need to equally service all these requests from all the application in a fair way, right? The fact that if you keep sending requests from core 1, which means that all these requests from core 2, core 3, and core 4 has to wait, right? This introduces the queuing latency, the additional time that you have to wait in the buffer that can lower system performance. So the controller's job is to make sure you mitigate this problem. You schedule them such that all the processor feels like they're not waiting for too long. Any questions so far about the goal of the memory scheduler? Let's talk about scheduling 101, right? So we know about the timing constraint, right? We know about number of all the incoming requests, right? Because it's the number of requests in the buffer. We know about the number of banks, right? So the design of memory scaler can be pretty complicated because you have to compare a bunch of things. But the basic goal is this. You want to have maximum number of row buffer hits, as we said earlier, right? Make sure application progress fairly. So the first set of works actually done by my advisor back in between 2006 and 2009. I forgot the year exactly. That's around the time that people realized that, hey, this thing exists and you can do something with it. But the paper talks about, hey, you can be fair across different applications too, because that leads to better performance. And make sure all your DRAM timing are satisfied. Right? Otherwise, DRAM will not function. You have errors. So we will now move into different scheduling policy. The first policy we'll talk about is called first ready, first come, first serve. And the slight caveat is the term first ready is kind of technically wrong, because the author of the paper kind of meant it's not first ready to be scheduled, but first row hit. You want to maximize row hits. First come, first serve is a policy that is used in computer science nowadays in many, many things. So anyone want to take a guess what first come, first serve mean? Basically, the order of the service is based on time of arrival, right? You arrive first, you get service first. It's kind of fair. But because we know that row buffer hit request is good, right? It takes less time. So rather than just do first come, first serve, you look at the buffer and prioritize request to the hitting row, followed by orders first, right? Does this policy make sense to everyone here? You first check, okay, do I have row hits? If I have row hits, compare between all the row hit requests. Whoever arrived first, you service that first. Otherwise, first come, first serve. I'm sorry about the noise in the background. My cat is in the litter box and it's getting louder and louder. I think she's digging up litter. If it's too loud, let me know. But otherwise, she'll be done soon. What can go wrong with first ready, first come, first serve? What can go wrong? Let me give you one example. I have two applications. So if I have first ready, first come, first serve, what will happen to these two applications? Who always get service? App 1 or App 2? Who will get the priority to use DRAM? App 1 has really high row buffer locality, all the requests going to the same row. App 2, the other way around. All the requests are going randomly into multiple rows. Who will be prioritized? App 1 or App 2 if I use this policy? Everyone can see is App 1, right? Application 1 will always be service. Application 2 will be waiting forever until the request from App 1 is not in the buffer. Then App 2 is like, okay, my time to be service. This is a big problem because actually the paper I showed earlier, the STFM paper, actually there was a case study that run MATLAB and C, and it turns out the way my advisor programmed it is to make sure that one of the application is really having high row buffer hit rate, the other one is not. if they run each of these two programs alone without the other program, they're fast. Both of them are okay. Performance doesn't suck. Somehow, if you need to run both of them at the same time, one of them will be about 7 times slower, while the other one is only 1.2 times slower. This is unfairness problem, right? One of the applications get unfairly slowed down because of their characteristics. So we can ensure some fairness with our memory controller. Actually, this is one of the bigger topics between, I would say, 2008, 2009, up to 2014, about 5 years long. My early works on for my PhD actually focusing on this problem for a CPU and GPU, the processor with the integrated GPU. So if you blindly prioritizing row hit requests, the problem is this is unfair. Right? This can be unfair. As I said earlier, so the solution is you can consider each application progress. How far am I from the finish line? And prioritize the application is still further away from the finish line because I never got any service. So you can ensure performance with scheduling because row hit requests doesn't mean they are critical. They are just faster to be serviced, right? What you need to consider is which instruction stall my pipeline. Go back to our processor design, right? You want to make sure there's no stalling. That's the worst thing you can happen in your processor. It just happened that the DRAM request is likely to stall your pipeline. What you need to do is find that request that stall the pipeline and make that request fast. Service them as fast as possible, right? So you actually need to consider, right? What make application faster? Which requests are likely to stall the pipeline? Which requests are likely to have more dependency, and which requests are likely to be more important? This is actually one of the actually multiple papers on week 12 would talk about this topic. There are many things you can do with memory scheduling. You might have realized a bunch of like share co-authors because a lot of these were coming from my advisors group on this topic back in the day. Right now, he's kind of moving to DRAM reliability and how to make sure DRAM performs similarly with the size that are growing. Any questions so far for memory scheduling? I can talk into multiple policy that have been introduced. If you're interested toward the end of the class, so I'm gonna have the last lecture slot. Basically, maybe 2 hours of that will be an empty slot. I'm gonna have a poll on which are the topics that you might be interested at. I will not briefly, 2 hours long, but talk about the topics that are being discussed, some of the state-of-the-art techniques on these topics, right? So if you have any question, ask me now. If you have any additional question, you feel free to use Discord, feel free to use email. I'll get back to you. Any question before we go into memory mapping, which govern how you place all the data across DRAM, how to get more bank level parallelism. All right, so once we are done with scheduling, the next subtopic under DRAM and memory management is how would you place data across DRAM? Right? DRAM is big. When you do allocation, right, the data can reside into the channel, rank, and banks, right? Which means that there must be a way to systematically store all the data across all the DRAM structures, right? This is called memory mapping. And there are trade-offs between how you map, right? So one of the idea that we can do is, well, if you look at how you use the memory, it's likely that the lower bits for the address are going to increase, right? When you go into the loop, for example. So you can interleave data in a certain way to increase DRAM parallelism. The textbook method that a lot of the paper assume are either cache block interleaving or bank interleaving. For cache block interleaving, it means that, hey, the idea is now that you know the cache block size, right? Let's put those index bits into different DRAM banks. Map them to different DRAM banks. What could be the potential benefit of this? Sequential access through multiple cache blocks will now go across bank 0, 1, 2, 3, 4, 5, 6, 7, right? What's the benefit in this? What's the benefit in striping across cache block? So cache block 0, cache block 1, cache block 2, cache block 3, cache block 4, 5, 6, and 7 will go to bank 0, 1, 2, 3, 4, 5, 6, 7. So the benefit is if you loop, basically if you do something like this, if you loop by accessing adjacent things, right, things that are next to each other, they are likely to be serviced in parallel because the next cache block that you have to access, well, they go to a different bank, so you can issue those cache block access right away, right? Another method is called row interleaving. Group sequential data on consecutive row across multiple DRAM banks. It's a consecutive cache block. Now it's consecutive row. Row is bigger than a cache block. Row is bigger than a cache block. The reason why this also can work well is within the same row, if you have streaming, basically you stream through addresses of data that are next to each other, the same volume. The next cache block over here will be mapped to the same row, right? So they have row buffer hits. All right, so first of all, if you have the next cache block, they are going to the same row. So they have row hits. This is 10 to 12 nanosecond, which is good enough, right? But access to consecutive row will go across different DRAM banks. So if you randomly have access to a totally different addresses, they are likely to be at the different banks. Right? So consecutive row span across different banks. This way you get the benefit of the row buffer hit rate and parallelism of DRAM banks. Any questions so far about the two policies? All right, so the next set of question is, okay, now that I talk about many things in DRAM, what else can we do? Right, what else can we do? With the mapping, I mean, because we designed the hardware, technically you can place this any way you want, right? You can also use a combination of the bits to XOR or do something to further spread, basically spread out DRAM accesses across multiple channels and multiple banks. And you can also even do something like this, physically partition portion of your DRAM through what we call page coloring, right? Basically, this means that the OS would work with the hardware and figure out, okay, these pages, the page from the virtual memory lecture, the page would go to different parts of DRAM banks. It can only access access bank 0 to 3. The other group of pages would be bank 4 to 7. Those are possible. The reason why you might want to do this is to make sure that two applications will not interfere and slow down the other application. So this would reduce interference, can potentially improve the performance, but you need to do the management well. Right, so let's do a quick example and put everything together. And let's consider following timing, right? 2 channel, 8 bank, 2 ranks, 4 kilobyte row size. And here's the DRAM timing, 10, 10, and 10. Pre-charge 10 cycle, activate 10 cycle, and read and write also 10 cycle. With the following sequence, time of arrival, read or write, and this is the address, right? If I use cache line interleaving, how much time would it take to finish these, how many? 1, 2, 3, 4, 5, 6, 7. 7 requests. So first thing first, this is, let's say, row A, right? What are the other requests that are also going to row A? For sure, this is the one, right? Because you know that it's 4 kilobyte. First log of 4 kilobyte, that's 12 bits. Which means that the last 3 digits, oh no, not the last 3 digits, but if you look at the address without the last 3 digits and they are the same number, it means they go to the same row. This thing is to row B. This thing also go to row B, right? They are literally the address next to each other. This thing go to which row? A or B? This is go to row A, right? Because it's 12 bits. So it means the last 3 digits. This is row B and this is row A. Any questions about which row they are going to so far? All right, so the next question, what banks are they going to, right? You have 8 banks and you do cache line interleaving. Cache line interleaving means that adjacent cache block go to different bank. So if you look at your address and it's 64 bit machine, so 6 bits is for the byte in block, right? 6, right? Yeah. 6 bits are being used for the byte in block. There are 8 banks, so the next 3 bit is for the bank bits. Let's say this is going to bank A. Let's say that is going to bank A. Who else are going to bank A? I'm going to use a different color so that you can clearly see the bank and the row apart from each other. So this is bank A. This also go to bank A, right? Because that 3 bits is in the the second digit and the third digit in my hex number is 0, 0, definitely going to the same bank. This is also bank A. Same bank for sure. What bank does this go to? 101. 0, 0, 0, 1, 0, 0, 0, 0. So this is going to bank 4. Wait, bank 4, which is actually, I'll call this bank B. Bank A is bank 0. This is also going to bank 4. Because 7 is 111, right? 0, 1, 1, 1. The last one is the last ones here is a part of the bank bits. What is C? C is 1100, right? So this is going to, so this is bank B or bank 4. This is bank A again, or bank 0. So there are two banks, bank 4 and bank 0. Some requests will go to row A, some requests go to row B. With the time of arrival, right? I'm not sure how to fit this in the page anymore. I kind of need a whiteboard. But the first 3 requests, actually the first 4 requests, no, 5, within this 15 cycle range, right? So those are going to be considered together. There are 3 requests to bank A, 2 requests to bank B. Let's look at bank A first. The first 3 requests are going to bank A. The first 3 requests are actually going to bank A. So you have, so bank A is like this. You first have request to row A, right? Followed by a request to row, which one are you servicing first? You need to first service this. It's the first request that arrived. DRAM is empty. No one else is in my schedule, the request buffer. So you service them right away. Followed by a request to row B. Followed by another request to row B. Right. So these would take 30 plus 30 plus 10. Pre-charge activate read for the first request. Pre-charge activate read for the second request to row B. The third request also go to row B, so it's only read and write, don't have to activate, right? So these are the first 3 requests to bank A, row A and B. The second set of things go to bank B. I'm gonna use a different color here. This request and this request at 10 cycle go to bank B. Right? They go to bank B. Row A followed by row A. So that would take 30 plus 10 cycle. Right? The third request to bank B will come in that go to row B. So this is that request here, go to row B. The last request, go back to bank A. Go back to bank A. So I'm gonna use a different color for the last request. Sorry for so many color. I'll use an orange color here. This request, bank A, row A. Bank A, row A. So after this thing happen, you go to row A. So you add 30 more. And that's it. Bank A service request to row A, followed by row B, and followed by row A. 30 again, because you need to switch from A to B. 10 because it's B to B, 30 again because you need to switch back from row B to row A. So that in total, 80, 100 cycle. You finish all this thing for bank A. Bank B, there are 3 requests to bank B. The first request arrived at cycle 10. That goes to row A, followed by cycle 12, also go to row A, so that's 30 plus 10. At cycle 50, when you finish servicing these 2 requests, another request arrived to row B. So that's another 30 cycles. So at cycle 50, you add 30, that's 80. So at cycle 80, everything finished for bank B. Any questions so far? Any questions so far? Because I feel like I need a whiteboard. So if you still have questions about this particular example, drop by on Wednesday. On one of the Wednesday, I'm gonna be in the office. I'll go through this with more room that I can draw inside my office, and I promise you it will be more clear. Basically, the steps here are figure out what bits are the bank bits, then figure out what are all the requests going to. Are they going to the same bank? What row are they going to, and what channel? In this case, it's they go to the same channel 0, because the channel bit, I haven't specified that. I kind of forgot. So let's assume they go to the same channel. Any questions so far before we go into the DRAM reliability? All right, so if there's no sorry. If there are no questions, again, as I said, we are wrapping up the memory scheduling topics. So we just cover how DRAM works, what's the DRAM cell, what are the DRAM operations, followed by how do we actually schedule all these requests together. We went through one example that is kind of messy on the slides. Let's take a quick break, 10 more minutes. So let's meet at 11:05, and we'll continue on to emerging. This is actually one of the emerging area in DRAM research. I wouldn't call it emerging. It's been around for a while, but it will get more and more complicated as you have bigger and bigger DRAM. Bigger and bigger DRAM means fewer and fewer electrons on my capacitor, which means that many things can go wrong. Your data can be corrupt easier. So we will talk about how do we combat and actually get better at making reliable DRAM. So we'll talk about this and then followed by some of the different memory technology that are going to come out. Some of them came out in the last year that you can buy. It's on the shelf these days, and they're pretty exciting. It would somehow not changing quite a lot, but it would change how you think about the memory a little bit. How big can it be? So let's take a break. We'll meet at 11:05. If you have more questions, you can ask me when we are back at 11:05. All right, so let's take a quick break. All right, now we are back. Okay, so let's now talk about what can go wrong with DRAM. And many things can go wrong because you're not really storing a lot of electrons inside DRAM. This basically means that you can have errors from reading DRAM cells. Generally, DRAM consists of a transistor and a capacitor. That capacitor loses charges over time. So it means that you need to periodically rewrite data into all the DRAM rows. Otherwise, your data is gone. Yay, electrons is gone to the ground and it leaks out. So that's the first thing that you have to ensure. The second thing you have to ensure is there's this thing called faults, right? Sometimes the cells are permanently damaged. These are called hard faults. Basically, you cannot really do anything with that. That DRAM cell die. There's also soft error. Soft error means that sometimes it just happens that electron lose enough charges that it slipped a bit. Or some other cell induce the magnetic field that draw electrons into the neighbor cells. The electrons go into the cell, the bit flip from 0 to 1. Yay, you change the value of your data, right? So let's talk about the first problem. DRAM loses charges over time, right? It leaks to the capacitor, right? As you can see here, this is full. After you pre-charge, everything is full. What actually happened is because these are capacitor, right? Capacitor charges is going down over time, right? As time go on, charge, it goes down like this. Oops. So basically something like this. But let me draw a little bit nicer curve here. Not laser pointer. Something like this. So at some point over here, you need to recharge your capacitor. You need to recharge your capacitor, which means that as charge here leaks out, you need to make sure it doesn't leak out to the point that it go below half VDD. Otherwise, you read a wrong data, right? This process is called refresh. And the process refresh is basically do the pre-charge. You connect the cell so that the electron moves back into the capacitor, right? So that's what the RAM refresh is for. Once in a while, the controller needs to write the same data over the same DRAM cell to make sure that you maintain the data. There's a timing called TREFI, longer acronym. REF is refresh, I is interval, time refresh interval. This determines the frequency that you need to rewrite everything back to DRAM. Right? This process called DRAM refresh. And during this DRAM refresh, the bank becomes busy. It means you cannot service any normal read or write request, right? So what happens if I increase the size of my DRAM? What will happen? This means that I'm going to spend more and more time doing the refresh, right? DRAM will be taking more and more time being offline because I need to refresh. So if you don't do anything with how DRAM refresh, at some point you can't have big DRAM, right? You cannot have a large capacity DRAM because they'll end up spending most of the time refreshing. So there are multiple ways you can reduce the overhead of DRAM refresh, right? Because basically the first idea is, well, do you have to refresh every single thing at the same time? The answer is not, right? The answer is not. So the first idea is do that in small bursts, leave enough room for a normal operation so that you don't block DRAM off for a long time. you do refresh a few rows at a time. The benefit here is this allows you to actually squeeze in normal DRAM operation and squeeze in just 1 or 2 or 4 or 8 rows of DRAM refresh. There's the concept called auto refresh that groups rows that are refreshed and they will be done automatically at a time. Another idea is, well, one of my friend in a group actually went back in CMU asking this question. Well, does the cell lose its charge at the same rate? And the answer is actually no. So one thing you can do is you can profile how fast each DRAM cell lost its charges. Then you can refresh based on this profile. And this is a paper presented at ISCA 2012 by my groupmate. And the benefit here is you can delay, right? You can delay how long you can refresh based on the profiling information. It turns out only a few cells has to be refreshed every 64 milliseconds. Most of them is between 128, 190 something, and 256 milliseconds. So you can delay the refresh interval. What are the downside? The same guy actually keep doing this experiment and now kind of find that, hey, what we found earlier is not exactly true. There are some data on the retention time that actually doesn't turns out that DRAM device has such a diverse pattern. So still, the overhead refresh can be delayed. So basically, you can identify the bad cells that has to be refresh at 64 milliseconds and make sure those are done at 64 millisecond interval. But then for the rest, you can, if you can find where are those cells, you can refresh at different interval. There's also many other works across a few research groups in the world that looks into these issues. You can look at paralyzing refresh with accesses. This is done also by my friend. He sits actually next to me in the cubicle at CMU. He was working in basically DRAM and DRAM microarchitecture, including refresh. There's also another method to make retention time aware of DRAM behavior. Also, then you can also improve things like pausing the refresh, reducing the power it requires to do refresh, or mitigate other overhead using the software, the operating system. Right? So if you're curious about any of these topics, I will go into the detail in the second semester. So what happened is usually for these topics that are really recent, like in the last 10 years, we'll cover this paper, these state-of-the-art techniques. What do they do? Why do they achieve what they achieve? What are the current design in computer? And how can you take advantage of new types of hardware in the second class, the advanced computer architecture? Now that we talk about refresh, capacitor lose charge over time. Let's talk about the second problem. DRAM errors. There can be inaccuracy when you read DRAM cells just because there are so few electrons. So how can we detect or try to retrieve the correct value, right? There's a big area of research called error detection and error correction. How many of you noticed some DRAM that you buy is called ECC DRAM? Or have you seen this before? The word ECC. So if you look at different DRAM, the one that would go into server, the one that go into server and data center, they are typically ECC DRAM. ECC stand for error correcting code. It allows you to correct some of the error. I believe right now you can correct up to like 4 to 5 bits of error, and you can detect around 6 bits of error. So if you start to detect that many errors, you say, hey, this is probably not safe. Something is wrong. I'm going to reboot myself, and you run into blue screen. So I hope you have seen that before sometime when the server reboot or run into blue screen or memory corruption or something related to memory errors. There are multiple ways to correct errors, and one of the most common is you can add more bits to correct and detect error. Today we'll talk about one of the it's more like a textbook method to correct the error called Hamming code. In the ECC DRAM and newer technology called IECC is also error correcting DRAM, error correcting code in DRAM. They are a lot more complicated that involve a lot of math. So right now, let's talk about the basic concept called the Hamming code and SecDet. SecDet is called single error correction, double error detection. It means that I can add these bits, which allow me to correct one bit of error automatically. Or if it happened that 2 bits flip at the same time, I can detect that. The idea is to add additional bits to detect any bit flips by using XOR. And we'll go through the example of how this works. Each additional bit is called the parity bits. The word parity is used a lot of in computer science. Over here is the additional data to check the integrity of your data. Multiple of these parity bits are used to detect location of your error. As I said, SecDet stands for single error correction, double error detection. There are, let's say you have 64 bytes, or let's say 64 bits word. The number of parity bits is going to be log of the size of the word plus 1. Basically, if you want to encode 64 bytes, then it's going to be log of 64 bytes plus 1. Log of 64 bytes is 16, so you need 17 parity bits. That's quite a lot to correct one error. That's why there's additional method to correct 4 or 5 errors based on different encryption technique. Over here, we requires log of n plus 1. The reason why it's 16 is 64 bytes is 64, no, my bad, it's not 16. 64 bytes is 64 multiplied by 8 bits. So that's 9 plus 1, that's 10 bits. I do the math wrong, I'm sorry guys. So for 64 byte data, you need 10 bits. So let's do an example on how SecDet works and the magic of SecDet. Over here, let's look at the top table, which show how it works. And this is 8-bit data. Right, there are bit 0 to bit 7. Those are all the data. These are the parity bits. The way you do this, how SecDet work is for each of these bits. When I have the letter X, it means that I'm going to XOR everything highlight with the X. So this 8-bit will XOR every bit. These XOR every other bit. As you can see here, bit 0, bit 2, bit 4, and bit 6. Over here, you XOR every other 2 bits. You XOR bit 0 and 1, 4 and 5, and this would XOR every other 4 bits. So as you add more bits here, you can see that if you need to add one more parity bits, then it's become grouping between the next every other 8 bits, the next every other 16 bits, the next every other 32 bits, right? So I'm going to erase everything here so that I'm gonna not make a mess of this slide. So over here, you XOR the entire thing with different color. The next parity bit, you XOR this bit, this bit, this bit, and this bit. With the next color, blue, over here you XOR this bit and this bit. And this color, black, will XOR these 4 bits. Now let's switch back to orange. So, given the pattern down here, there are 4 set of 8 bits data. Let's do one at a time. So what's the XOR, what's supposed to go here? Is it a 1 or is it a 0 if I XOR everything? 1 XOR by 1 is 0. 0 XOR 1 is 1. 1 is XOR. It counts the number of ones. If the number of ones is even, that's a 0. If the number of ones is odd, it's going to be. So is this a 1 or a 0 if you XOR everything? 0. There are 4 ones, it's odd, number of ones, so that's 0. What about this bit? I now have to XOR this, 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 and this. Is that a 1 or is that a 0? That's 1 right here. That's 1 right here. So that's a 0. The third bit is going to work this way, right? You are going to XOR this bit, this bit, this bit, and this bit. There are also, again, 2 number of ones, so that's a 0. And the last bit is 1, because it's the first 4 ones and zeros. So the purpose of these parity bits is this. Let's say I have the error. Let's say I have an error. These things change to 1. This thing changed to 1. How can I detect that this thing now changed to 1? I'm going to change the ink color to red, right? If bit 3 changed from 0 to 1 through an error, what will happen? This parity bit will not check out, right? Because if you XOR everything again, this is supposed to be 1. Right? If you XOR everything again, it's 1, 1, 1, 0, 1, 0, 0, 1. There are 5 ones. So it's supposed to be 1, but somehow I store 0. Right? So you first now detect something is wrong. For sure, something is wrong for sure. The next parity bit, which detect this, this, no, this one, and this one, right? Is that correct? That's 1 here. That's 1 here. The number parity bit should be 0. So everything is okay. Hopefully everything is okay with bit 0, bit 2, bit 4, and bit 6, right? Everything seems okay here. Everything seems okay in bit 0, 2, 4, and 6. Because my second parity bit tells me so. It's 0, and it's supposed to be 0. So nothing is wrong here. But I know something is wrong, definitely, with my data. Now let's go to the next set of parity bits. Let's look at this bit. This bit will check this 2 number, this 2 number, and again, it's supposed to be 0, and I got 0. Right? So this checks out. Nothing is wrong. Nothing is wrong under this bit, this bit, this bit, and this bit. So the first parity bit tells me that this is okay, this is okay, this bit is okay, this bit is okay, and this bit is okay. The second parity bit checks that this is okay, this is okay, this is okay, and this is okay. Right? Let's look at the last parity bit. Let's look at the last parity bit. Over here is 1, and it's supposed to XOR this, and this. And now this thing is 1, right? So look at this bit. You got a value 1, but it's supposed to be 0. So you can ask like, okay, something is definitely wrong with the first half of this. Something is wrong in here, right? Something is wrong in here. Either bit 3, bit 2, bit 1, and bit 0 might be wrong, but the parity bit 10, 9, 10, and 9 already rule out bit 0, bit 1, and bit 2. So there's only one place that is going to have bit flip, which is bit number 3. So you know exactly this is supposed to be a 0. Based on the value right here, it can tell that, hey, bit 3 is supposed to be a 0. So that's definitely that bit flip over here. So you can correct from 1, you correct it back to 0. That's my original data. So the parity bit tells you, first of all, whether there's an error, right? Whether there's an error. Then it tells you what is the location of my error. So once you know that one bit that flips, you can flip it back, correct the data. Any questions so far before we go through the next example? There are 3 set of data left. So over here, I'm gonna do this example, this flip to 1. If there's no question yet, so let's do the parity bit for the second set of data, right? Over here, if you XOR everything, you get a 1. If you XOR bit 0, 2, 4, 6, you get 0. If you XOR bit 0, 1, 4, and 5, you will get 1. And if you XOR the last 4 bits, you get a 1. So that's the parity bit for the second set of data. Now let's assume this. Let's say this thing flipped to 0 and this thing flipped to 1. You have 2-bit flips. You have 2-bit flips. What will happen here? I'm going to use the color blue so that you can tell the difference. This thing will check out because there are 2-bit flips. The parity bit that XOR every single bit would be correct. Right? It would be correct. Then you check the parity bit here by XORing this bit, this bit, this bit, and this bit, right? 1 XOR and 1, 1, 1, 0, 0. And that is a 0. So this bit is also correct. This is also correct. Then you check out the third bit, the third parity bit. So you're gonna check this bit, this bit, this, my bad. You will then check these 2 bits and these 2 bits. 1, 1, 1, 1. That is a 0. So you check the parity bits and it's wrong. So you know something is wrong here. Then you check the last set of bits. You then get 1 here. So that's a correct bit. Over here, the 8th bit, which XOR everything is correct. It means that that's a 2-bit error. That's 2-bit error. I don't have information to correct both of the bits. There's no way for me to flip both the bits and tell exactly which bit has an error. But I can tell there's something wrong. Something is wrong here because if nothing is wrong, all the parity bits should check out. It should be correct. Somehow this bit is not correct. It means that there are 2-bit error. What the OS would do here is to either crash the program that used the data. If that program is your kernel, reboot and blue screen. right? So basically you have to have a way to terminate this program because there's some error. That error can be dangerous. So the OS will figure out how to terminate this running processes. Let's look at the third set of data. 1, 0, 0, 0, 1. This is going to be 0. The second bit would be 1, 0. This is going to be 1. The next set of data should be 1 again, and this is 1. So that's a parity bit for the third set of data. Let's say I have a bit flip right here from 0 to 1. Which parity bit would be wrong here? If that's the case, if I have bit flip at bit number 4. Obviously, this would be incorrect. Yeah. So bit 9, 10, and 11, which one would be incorrect?
Nine, 10.
9 and 10, yes, you're correct. So this will somehow add to 0, this will be 0, and this is correct. Right? 9 and 10. The reason I can tell 9 and 10 quickly is if you look at this table, if you look back at the table, you will know that if you have a bit flip at bit 4, which cover these bits, right? So you will look back at the row and you know, okay, this bit's going to be wrong, this bit's going to be wrong, and this bit's going to be wrong because I XOR that one particular bit. That's actually a systematic way to tell which is the wrong bit, which is the wrong bit, actually. Over here, if you have 9 and 10s that are wrong bits, what you can do is you know that 9 and 10s are a part of the fourth bits, right? The fourth bits. 1, 0, 0, the bit 11 is correct, bit 10 and 9 is wrong. Correct, wrong, wrong. If you represent correct with 1, wrong with 0, 1, 0, 0 is 4. 1, 0, 0 is 4. So you know it's the fourth bit. From this example, which I would use the orange bit, right? Orange bit 3 is wrong. Bit 3 is wrong. What you got from here is wrong, correct, correct, 0, 1, 1. That's bit 3. Let's do one more example here. This is going to be, let me use a different color. Which one should I use? Green. 0, right? If you XOR every other bit, 0, 0, 0. I think this is all the case. So if I have this particular bit pattern and I have a bit flip right here, this change from 0 to 1, which bit will be wrong? Which parity bit? This would change from 0 to 1, right? And this would change from 0 to 1. This is correct, correct, wrong, right? 1, 1, 0. That number is 6. So you know it's a 6 bit. So the parity bit that's correct is 1. Parity bit that's wrong is 0. You know from that binary pattern, you know which is the position of the incorrect bits. Over here is correct, correct, wrong, 1, 1, 0. 1, 1, 0 is 6. So you go to the 6th bit and you can now identify the bits that is flipped. There is a actually there's a reason behind this. The reason behind this is the wrong bits will cover, right? It will cover that particular location. So if you have the wrong bit, it tells you where to jump in this bit pattern to find the correct wrong bits. Any questions so far with the secdet example? Out of curiosity, have anyone here seen this before? Okay, good. This is kind of like a sophomore level digital design knowledge. So I'm glad that this is the first time you've seen this. So what my message here for this slide is that when you have errors, when your data have errors, there are ways to encrypt your data by adding more information so that you can correct the error. This is a pretty common technique, not just in hardware. You can add some tolerance toward errors by adding additional piece of information. So another thing you can do is pushing DRAM towards its limit, right? DRAM timing that we see guarantee to give you correct data. How many of you heard about this thing called overclocking? You might have heard the word overclocking. What they are actually doing is overclock means that I'm going to make the clock faster, right? Typically, you can make the clock faster. Change the configuration and it will make the clock faster. When the clock are too fast, you will not have enough time to get your data. So you can overclock a little bit, make your processor maybe 5% faster. I don't really recommend you to do that because it generates more heat. And a lot of time your CPU is not totally designed for that unless you have another cooling, a good cooling system. But then you can overclock to make everything faster. Another thing is DRAM cells, as I said earlier, that apply to refresh and access time. They're not equal. Some of them are faster than another. So if you want to make DRAM faster, you can, I guess, first of all, overclock the DRAM. Modify the configuration in your memory controller to make it faster. You can selectively overclock and oversupply the input voltage because if your voltage is higher, it means that electron move faster, right? So you can overclock and oversupply DRAM to make it faster. You can make DRAM to consume less power in all your laptop, iPad, mobile phone, tablets. They all use this thing called low power DRAM. LP, low power, DDR, DRAM. These things consume lower amount of power. Obviously, they cost more, right? And they are less likely to be big, as in like the capacity, but it consumes a lot less power that allows your phone to last an entire day. Hopefully, most of the time when I use my phone, if I play games, that will not last a day. But still, these low power DRAM helps quite a lot. There are also other memory technology that's advanced in the material science area that emerge into circuits and going into architecture that allows you to do many fancy things. These days, you can buy a GPU that has DRAM tiled next to each other. They are going to provide more bandwidth. On top of this, you can even do something like 3D stack DRAM. So you have DRAM, right, in 2D. You can put them on top of each other and then connect this to a wires. It's not exactly a wires. We call this through silicon wire. It's a substrate that allows you to transfer data across different stack here. The 3D stack DRAM give you way more bandwidth, a lot more bandwidth. So this is common. It is going to be common in the GPU coming out. High-end GPU these days already come with 3D stack DRAM. They will have a lot more channel. So the number of memory channel is going to be a lot higher. You can have non-volatile memory. Non-volatile memory will consume less power. They are going to be almost as fast as DRAM, but they are way bigger. The types of non-volatile memory right now that are common are phase change memory and STT-MRAM, the memristor, or sometimes there's also RRAM, resistive RAM. which some people, including myself, are using this RAM to do matrix multiply inside the RAM itself. Because the way it reads the data is V equal IR. And I multiplied by R is matrix multiply. So I can use that for matrix multiply. So let's talk about TG stack DRAM. Basically, it's a multiple layer of DRAM chip on top of each other. It provides higher capacitor per the area. Right now, the current generation of AMD GPU, I think this data might be a little bit too old. This is old information. These are, I think, that are capable of doing 3D stacking for sure, and high-end graphic cards that are used in the server who have 3D stacking. Layers connect through silicon via TSV, as I said earlier. A lot of internal bandwidth, a lot of external bandwidth. In your typical 2D DRAM, you have a lot of internal bandwidth, not a lot of external bandwidth. Over here, you have a lot of external bandwidth going off the DRAM chip into the processor. And this can be put on top of the processor too. So it's possible to have the compute element within the package, allow for the things called processing in memory. You have the processor in the CPU. Processing in memory is another school of thought saying, hey, well, you have a CPU, right? But sometimes your data, your computation is really closely tied to the data. So you can add some logic inside DRAM. You can do some simple computing, right? So what can you do with PIM? It offers some basic logic. Think of simple ALUs that next to the memory elements. This gives you much higher bandwidth, lower data transfer. We show back in ASFOS 2018, this is a work I've done with my colleagues that show that if you run Google workload in a consumer devices like mobile phone or tablet, there's a lot of benefit in some certain cases that can be done on processing in memory. There are also complications. You need things like memory consistency, which you're going to learn soon in the next lecture or 2 lectures. Actually, in the next 2 lectures. Next lecture, I'm going to talk about the GPU. We need to figure out where and when to execute this in PIM. So this is a follow-up work by my colleague. I'm the co-author of this paper as well. Basically, we look into how to actually enable efficient near data accelerators by optimizing data movement. And on the topic of PIM or near data accelerators, I just had another paper that I co-authored with many of my colleagues in Zurich, CMU, Intel Labs, and where else? Bilkent in Turkey, and UIUC and Facebook. So basically, we introduce the substrate and obviously TGGS. So as you can see, there's so many authors. We look at genome DNA sequencing over here. You want to basically detect things like deletion, substitution, and insertion. And what we found is that, well, a lot of this process can be done. Where's that figure? Let me find that figure real quick. So a lot of this process can be done within the stack DRAM, right? So you can add some logic here that are relatively simple, Talk to the main memory and allow the processing element to talk to the memory parts and get a much higher throughput and a lot of power saving. So if you look at the throughput here, we get around hundreds of times better and quite a lot more efficient. So this is a concept called accelerator designs. We come up with the hardware that performs certain tasks that are important or slow at the moment. Design a new hardware and make it run a lot faster. Over this paper, in this paper, we basically minimize things like data movement to get that benefit. And this work just been presented, I think, 2 weeks ago in Micro 2020. There's another concept called non-volatile memory, where cells are not really based on capacitor, right? So it doesn't leak over time. This is denser than DRAM. You get a lot more capacity per area, and you don't need to refresh the data. This applies to most non-volatile memory, and for STM RAM, you can refresh the data often to make it faster. There are some attempts to try to make this to replace the SRAM cache. I haven't really seen a follow-up work on that for multiple years now, so I guess it's still in the work, or it might not pan out. So another thing is this has a lot lower access latency than solid state drive. Even though they are similar in nature to SSD, they are really fast as DRAM, a little bit slower. But because they are similar to SSD, it means that writes to NVM are destructive. Think of it this way. Instead of having capacitor as a cell and you store electrons, some of these techniques shock the cell to change the resistance, change the property of the material. So if you are getting shocked again and again and again and again, at some point you die. Right? Think of it this way. Basically, the cell gets shocked too many times, it dies. So NVM are destructive when you have a lot of writes to the same cell. The benefit is a lot bigger, right? It allows terabytes of memory. Data is persistent. You don't use capacitor to store the data, so you don't need to refresh. You store the data and stay there forever. You can use this for data recovery. Somehow, if power outage happen, reboot the machine, everything is stay as normal. It's as if there's no power outage magically. It's possible, actually. No leakage power. These are one of the thing that consumes the data is called the leakage power. Data leaks out over time that consume power. Non-volatile memory data doesn't leak out, so you don't really drain the data that way. It doesn't drain the power that way. It can be used in combination with DRAM. So you can use DRAM or stack DRAM as a cache to non-volatile memory, such as the Intel Night Landing technology. There's also hybrid memory. You can combine DRAM and NVM together. There's actually multiple papers that looks into this direction for the last 10 years, actually 10 years or more. The hope is, can we get the best of both worlds? So you can use DRAM as a cache to NVM. There's already a paper in 2009 on this, and there's actually multiple papers on using DRAM and NVM together in single level. I have a paper with my colleagues actually in ICCD 2012. We actually got the best paper award from that paper that talks about how to maximize, be row buffer hit friendly for both DRAM and PCM. Before we leave today, because we only have about 10 minutes left, that's why I kind of rushed through and made sure we covered the side topics. I'll tell you one thing, the non-volatile memory part will not go into the big questions on the exam. The worst that can happen on 3D stacking and non-volatile memory will be open-end, like conceptual questions that I can ask. So if it's open book already, you can go and check out the slides here and learn more to answer the question on the final. That's why I cannot rush through this, just to make sure you have heard about the terminology, heard about some trade-off, and we are not going to dive into the detail. The detail we discussed in the advanced computer architecture class. Notes on main memory, because as I said already, a lot of things here, I'm basically introducing the basics. The state-of-the-art advances in architecture these days, a lot of them focus on the main memory. It's just a really active area of research. Always a submission that get accepted and get rejected on these topics. It's still a lot of people are working on this. Avoiding this long memory request latency typically lead to a really fast program. Works on high performance computing, works on program frameworks, APIs that you use and love nowadays. They all focus on limiting the long latency operations of the main memory. feel free to drop by office hour if you're interested in this area or enroll into the advanced architecture class, because we definitely will discuss these things for a while. Paper this week, anyone want to present before we move on to, actually, let me check if anyone want to present the paper that you read in this week. Otherwise, we'll skip this part and talk about the logistic on the project.
I think we just lost Sangpon.
Oh. Okay. Yay. It's okay. I have a meeting with him on Thursday anyway. I assume he will not present. If he needs to present or if he wants to present this week, I'll ask him to present next week instead. Project updates. Our final exam, I look at the calendar. Our final exam will be on, so the final exam period is November 23rd, I think, onward until December 4th. Oh my God, it's so hard to check. Yeah, November 23rd and December 4th. So your final exam will be on the 24th, November 24th. Let me write it here. After this exam, you will have 1 week to present and prepare your project presentation. This is on Tuesday, December 1st. Then, after your presentation, most of the grade will be from your report. This is a breakdown. Presentation is 20% of the entire project grade. Report is 80% of the project grade. What am I looking for? Presentation, this is basically how is your project. I'm not going to ask for like super novel idea or anything. This is not research methodology. For most of the discussion we have so far, you basically hit all the bar. If you do not hit the bar on getting full credit, you've been warned already, so you know who you are. One more thing that I need to make sure you are aware. If your presentation covers certain things, and I feel like there are certain aspects of the evaluation that you cannot answer, but you need to be able to answer that. Otherwise, I can't tell whether you're actually doing a project or not. I will ask these questions that are critical. And if I need the answer on your report, I will tell you, you need to be able to answer those questions on your report. If I don't specifically say that, you don't have to put that on your report. The rest are basically curiosity questions, things that I'll tell you, hey, you can improve the project this way or that way. I might specifically say, put that answer on your report. Otherwise, your project grade will tank because it shows that you don't know what you're doing. Because that happened last year. And it just happened that the report doesn't answer that question. So that's really bad. I need to tell you ahead of time. If I ask you to put certain questions answer on the report, do that. On the project report, 40% of the 100%, basically report is 80%, it's breaking down to 40, 20, 20. The scope and how you evaluate it, how you test your design, how you actually conduct all the experiment, how you write the program, these are 40% of your grade. Again, these need to be relevant to our class. If your project has nothing to do with the class, you've been warned and you need to come up with a new project. The other 40% is breaking into 20 and 20. 20% is the proposed mechanism. I just want to make sure these are scientific. You don't come up with a solution with no proper explanation. If you try to do something and you don't have a good data, that's totally okay. That's totally okay. You just need to be able to explain why that happened, or have some idea on how you will evaluate it, on why that might happen. I'm not asking for a full-blown solution. You are not writing a paper here. I just want you to basically find the process of finding the results, finding the explanation why the result behaves certain ways. So hopefully this helps. If the project is related to your master thesis, it hopefully helps answering some of those questions on the performance angle or from the more hardware angle. 20% is on the difficulty of the project. If I haven't tell you anything, you get 20% already. This 20% go from 20, go down. It go down. If I want something that, hey, this project is not okay, it's too easy or something, you are losing this 20%. So first of all, make sure your project is relevant. Otherwise, you lose that 40%. Make sure you prepare your presentation. Make sure you can answer what happened, why you see certain results. That's another good fraction on your grade. And make sure you make the project like master level, right? Wednesday, 11:19 p.m. At midnight on Wednesday, report is due. You cannot use the late day because I need to read your report and submit your grade by that weekend. Late submission, you get 0 for your report grade. Everything here, including the 80% of your project grade, basically becomes 0. Don't submit it late. Don't submit it late. I cannot. Okay, I will give you an example. Last year, advanced computer architecture class, there's a student that submit the report about a day late. And the grade dropped 1 letter from A to B. And it's sad, so don't do that. So please don't do that. This time I'm gonna be a little bit more strict because I think a lot of you have been progressing pretty normally, right? So you're doing really okay so far. Just don't sleep through the deadline or something. Please don't sleep through the deadline because that happened before and I feel really sad about it. And I can't even like find a way to contact the student. That's like sad, basically. Don't sleep through the deadline. Whatever you have on the Wednesday on your report, make sure you submit that. All right? Handshake. And then with the remaining days, because Wednesday midnight is due, so I will have Thursday and Friday to read your report and submit the grade. Hopefully by that Friday, you know your grade on Canvas. So you can question, ask me, okay, what happened over on your different labs, different assignment, different exam. Then I think I will have basically, this is right after 1 week after the exam, right? So I'm gonna make sure I grade all your exam by the project presentation day, so they can come in, look at your grades, look at your rubric or my rubric, and ask me if you have any questions on the final exam. Any questions so far about this class? Basically, that's it. And someone just pinged me on Facebook saying his internet was down. So I'll tell him what happened here.
For the project report, do we have the same or a similar template as in research methodology?
I mean, to be honest, I would kind of appreciate it if you can make it similar into organization, because I kind of thought through that template already, and it allows you to explain everything I am looking for. But on the research methodology template, I kind of focus a lot on novelty of your idea, right? Identify what's different. Over here, I would say you can feel free to cut back on that and feel free to like talk a little bit about your design, talk a little bit about what are the problems you're trying to answer. I would appreciate a literature survey. I will not demand a good literature survey because you are totally okay to re-implement certain things, right? So I would like to over here focus on the idea that you're proposing, the things that you're doing, and the result with some explanation of why you see certain things. And it's okay to say there are bugs in my code. If you can identify where the bug is coming from and how do you plan to address it based on the difficulty of those kind of things, right? I program quite a lot before, so I can tell which bugs are hard and which bugs are like, why can't you fix this? It should take you less than between 1 to 5 minutes. So I will be as fair as possible, and I will make sure if you put in effort, you will be rewarded. If you do not put in effort, you will fail. Any questions about the template? All right, so that's it for the class. Sorry, I am for 3 minutes over now. Thank you so much for attending the class, and I'll be in the office tomorrow. If you want to drop by to get your exam, please feel free to do so. If you have questions on the exam, I definitely recommend to arrive before 11 o'clock because I will have meeting 11 o'clock. My tomorrow's schedule looks really bad. 11 down to 3 o'clock. And then I need to leave campus earlier because I'm basically buying a house. So I need to go and sign a contract in the evening, I think. So I might have to head out earlier. So recommendation, come in early. Otherwise, come in next week on Wednesday. Otherwise, check with me. I think next week I'm relatively... No, I'm not free. Okay, my bad. My schedule looks horrible. So next week on Wednesday, I can do afternoon, and then I can do on like other days or so. Just let me know ahead of time so I can make time for you guys. Yeah. All right, that's it for the class. Please go and have lunch and enjoy the rest of the break for an hour until you have the next class. Bye. Thank you.
Thank you. Bye-bye.